Hello everyone, I'm Satheeswaran. Today I'm excited to present my internship project Microwave Oven using PIC Microcontroller. In this video, I will explain what embedded systems are, how a microwave oven works internally, and how I designed and simulated this project. So let's start. I completed my embedded systems internship at Emertxe Technologies Pvt Ltd, a well-known training and project consultancy institute based in India. They specialize in hands-on embedded systems and IoT training, helping engineering students build real-world projects with a mentorship from industry experts. Their programs are designed to bridge the gap between academics learning and industry requirements, and many students go on to work in core tech roles. Before jumping into the project, let's first understand an important concept. What is an embedded system? An embedded system is a combination of hardware and software designed to perform one specific task. For example, a laptop or PC is a general purpose computer. You can play games, write documents, browse the internet, and many more tasks. But an embedded system is task, task specific. It is designed to do only one dedicated job. Examples washing machine controller, elevator control panel, and a traffic light system, and of course, a microwave oven. In all these devices, you don't see a keyboard or a mouse, but inside a small computer is working silently. This slide shows the project title and the project framework. Before writing even one line of code in industry, engineers prepare a document called RDD, Requirement and Design Document. This document defines what the system must do, how the system should behave, what components are required, why this is important. Because if we start coding without requirements, we may build the wrong system. Here we define the scope of the project. The microwave system is not just about heating food. It also focuses on user interface and user experience. A good UI means the user always knows which mode is selected, what time is set, whether cooking is running or stopped. A good UX means a system is simple and comfortable to use. So my project ensures clear screen messages, easy keypad input, instant feedback to user actions. In real life, a microwave works with high voltage, high heat microwave radiation. Testing such hardware in a student lab is dangerous. So instead of real hardware, I used a virtual simulation environment, PICSimLab. PICSimLab provides virtual PIC microcontroller, virtual LCD, virtual keypad, and fan. And they behave just like real component, but safely inside software. So we can test logic, debug code without any physical risk. Shows the block diagram of your system. Let's understand each block. Matrix keypad. The keypad is called matrix keypad because it uses rows and columns. Instead of connecting one wire per button, we use the grid system. This saves controller pins, reduce wiring complexity. The PIC scans the rows and columns to detect which key is pressed. And the CLCD. CLCD displays 16 into 4 character LCD. The LCD shows menus, modes, time, temperature. It has its own internal microcontroller. The PIC sends commands and data to display characters on screen. So the LCD acts like the communication bridge between user and system. And the brain of the system, microcontroller, the main component of embedded system is the microcontroller. Unlike a normal CPU, a microcontroller already contains processor, RAM, ROM, input and output pins all inside one single chip. This makes it compact, low power, low cost, perfect for home appliance. In my project, I used a big microcontroller to control the entire microwave logic. So you can imagine the big microcontroller is a brain of the microwave. And now the important point, embedded system often work in your real time. This means that the system must respond immediately when required. Example, if a user presses a stop button on a microwave, the system must stop instantly. It can't wait 3 or 5 seconds to finish some background task. Why? Because it is a safety requirement. Such systems are called deterministic real-time system. So in this project, timers, keypad scanning, and display updates must work precisely every second. A microwave oven is a perfect real-world example to understand embedded programming, user interface, state machine, and real-time timers, hardware-software integration. Look at the system behavior. This project follows a state machine concept, meaning the system moves through different states, power on state, ideal or mode selection, parameter setting, cooking, stop or completion. The system cannot start cooking unless a mode is selected, parameters are set. This prevents accidental operation. And the CLCD start with power on message, display powering on microwave oven on CLCD upon system startup. And the second is cooking mode screen, display options, micro, grill, convection, start. Uh, this is selected via key 1 to key 4. And the first mode is micro mode. Micro mode means microwave cooking mode. In this mode, the user first selects power level, um, because in real world microwave, different foods need different power levels. The user enters cooking time, input validation, and start to clear and has to enter. This is standard practice in embedded UI design. So the user always has a way to correct mistakes, a way to confirm input. This improves user experience. And the second one is grill mode. Grill mode focus on the top heating element. Different from micro, no power level selection, only time. Blinking cursor feedback. While entering a time, the cursor blinks on the LCD. This tells the user input is expected here. Such small US feature reduce confusion, improve usability. And the third mode is convection mode. This is the most advanced mode. User enters temperature value, system enters preheating. Just like the real ovens, you don't cook food in cold ovens. So the system waits until target temperature is reached. After preheating finishes, system asks for cooking time. Only then cooking starts. This multi-step logic is controlled completely by software state machine. And the fourth mode is start. This is one-touch cooking feature. If user presses key 4, cooking starts immediately for 30 seconds. If microwave is already running, pressing key 4 adds 30 more seconds. This requires the code to monitor keypad even while timer is running. This is achieved using timer interrupts, non-blocking keypad scanning. This is the starting interface of a LCD. Power on and cooking mode. After powering on, it will shows the four modes. Power on message, which is system displays powering on microwave oven upon startup, and the cooking mode selection. User selects mode micro, grill, convection, start using key 1 to key 4. And the another interface is setting time and temperature. To set time, display prompts for a time entry minutes and seconds with seconds blinking. We use keypad 0 to 9 and has to enter and start to clear. Same as to set temperature for convection mode, display prompts for temperature entry degree Celsius. Same as keypad 0 to 9 has to enter, start to clear. The user interface for cooking and control screen. During cooking, time must update every second. This is done using timer interrupts inside PIC. Triggers every 1 second, degrees countdown, updates LCD. This ensures time is accurate, no delay or drift. And this is a preheating screen in convection mode. Displays preheating and remaining time in seconds during convection mode. And this is the MPLab IDE, which converts embedded C code into hex file. And these are the header files of microwave oven, and these are the source files. Uh, Then we will move on to simulation part. Lab, um, we can upload files in file section and the boards, and these are the microcontroller, and this is the other parts. And this is the clock frequency. Uh, I entered in 20 megahertz. This means 20 million operation per second. It is the heartbeat of the system. And we use LCD 16 into 4 LCD. And this is this is our matrix keypad, which allows user to enter the inputs. And this is our microcontroller, PIC16F877A. And this is the heater. First, I will reset the button. First, it start with powering on microwave oven. Then we can select the modes. We will see the modes one by one. First, to enter the micro mode, I will press 1. After that, it shows power equal to 900 watts. After that, I will enter the time. Let's say I will enter 5 seconds and enter. After that, the heater will stop. Then we will see the grill mode. Grill mode is same also. We will enter the time. I will enter 15 seconds. I can pause, stop, and resume by entering keys 4, 5, 6. I can pause the timer by pressing 5. The fan is stopped, and I will resume using 4. And the third mode is convection mode. It shows the set temperature in Celsius, and I will enter the temperature. Then it shows the preheating screen. After preheating, it will show screen to enter the time for cooking. The user will enter the time. Preheating is done. I can I can enter time for cooking. Let's press, sorry, 5 seconds. And the final mode is start mode. I can press key 4 to start. The counter is decrementing. I can add time using when I press key 4, it will increase the time by 30 seconds. And I can stop the process by pressing key 6, and it will back to the more selection screen. And these are the overall simulation, the basic of embedded systems. We understood that embedded system is a combination of hardware and software designed for specific tasks. We also learned how a microcontroller acts as a brain of such system, integrating processor, memory, and input-output on a single chip. Then we discussed why real-time behavior is important in safety-critical systems like a microwave oven. The system must respond instantly to user actions, such as pressing the stop button. Next, we moved into the project framework. We saw how in real industry practice, development always start with a requirement and a design document instead of jumping directly into coding. This ensures the system is well planned and error free. After that, we explored the system architecture. We understand the role of matrix keeper for user input and the CLCD for visual feedback and and the fan as output actuators. Each component works together under the control of PIC microcontroller. Then we covered the core functional logic of the microwave. We saw how the system follows a state machine approach, moving from power on to mode selection to parameter setting and finally to cooking. Then we discussed in detail the three major modes: micro, grill, convection, um, where power and time are set, and where time is controlled with visual cursor feedback, and which involves temperature setting, preheating, and cooking time. We also saw the quick start feature, where one touch instantly starts or extends cooking time, a common real-world convenience feature. Next, we looked at the user interface design. We observed how startup screens, placeholders, blinking cursors, and dynamic time updates create a smooth and user-friendly experience. And we learned that even simple appliances require careful UI planning. We also explored the simulation environment using PICSimLab by using virtual components. We safely tested our embedded logic without handling real high voltage microwave hardware. We configured the system clock, simulated temperature using potentiometer and verified real-time time accuracy. So through this project, we successfully combined embedded C programming, microcontroller interface, real-time timer handling, keypad and LCD communication, state machine-based control logic, and simulation-based testing. All of these are essential skills for an embedded system engineer. And the final thought is this project shows that even a common household appliance like a microwave oven is powered by intelligent embedded design. By working on this project, I gained practical experience in planning, coding, debugging, and testing an embedded product, just like in regular industry environment. And I would like to mention that I completed this embedded system internship at a Emertxe Technologies Pvt Ltd, an institute known for hands-on embedded and IoT training. Their mentorship and structured training helped me successfully completing this project. Um, with this, I conclude my presentation. Thank you all for your time and attention. If you